Hello there. In this video we're going to be taking a look at integration, basic integration. We'll look at the reasons why we do it and various different aspects of basic integration. So the first question is why? Well, the reason why, there's two main reasons. The first one is it's to go backwards. So if something's been differentiated, you can do an integration that will take you back a step. So if you've double integrated, which double differentiated, take one step back to a single differentiation, or if you or two steps back, because you can integrate twice. When doing nothing like that in this video, by the way, that's fairly advanced. The other reason is to find the area under the curve. So you know when you're doing your differentiation, you plot, it's to do about the plot of a curve and finding the gradient under that curve. Integration would tell you the area underneath that curve. So it could be physically the actual area, as in cubic centimeters, cubic meters, or it could represent something else, such as if you've got power and you integrate, it will give you the energy that's been used in a time period. So you could integrate from 0 seconds to 10 seconds and know how much energy is being used in that time. We're not doing that today either. That brings me to the next question, indefinite and definite integration. And we're going to begin with be looking at indefinite integration, and I'll explain that as we come to it. Definite integration is related to that second reason of integration that I mentioned, which is finding area under curves. Indefinite is more to do with going backwards a step, which is obviously where we're going to start. That's the simpler thing. Using tables, question mark, you may notice, is when I first started teaching this to college, I used to give my students tables of derivatives, standard derivatives, tables of standard integrals. And I've seen now that in the class we're only usually covering the basic ones. So by basic I mean polynomial type situations, trig functions, log functions, exponential of using the letter E functions, Euler's number. Those basic ones, it's not too difficult to memorize them, and anyway you can use your table of derivatives but just use it in reverse, and that is the way I tend to go now. So there's no need of tables of integrals for this until you get onto really advanced ones like the inverse of sine and the inverse of sec and these kind of terms. Okay. So we won't, no need of tables at this stage. And symbols, what do I mean by that? So symbols is the symbols that we would use for integration, and these are basically this symbol. Ooh, let's try putting the pen on. I think we'll do better with a pen. Okay, so this symbol, which you probably recognise, a bit scruffy that one, but this is the standard integral symbol. It's actually an old letter S in the old Roman alphabet. By that I mean the alphabet that's used across most of Europe, and of course these days most of the world. So it's your old S symbol. So if you go into old historic churches and they'd have bits of scripture around the side of the walls, it would be this kind of S. If you put a line across it there, you've got an F. So that's the old F. Okay. So that's where the symbol comes from. They use this symbol for S because it's to do with summing. You're adding together all the bits of area. Again, that's to do with the definite integration. And again, more than that to follow. But that's where it comes from. And the other symbol, the other thing we have to use is this, dx. Well, it doesn't have to be x. It's d, whatever the variable is that you're relating to. So it could be dt, it could be d theta, it could be d anything actually. So that's telling you what your variable is that you're integrating in relation to, otherwise you wouldn't know. So if you just had a number like 2, it'd actually gain one of these symbols and you wouldn't know which one it gained without that there telling you. When you get into more advanced integration, it does play another part as well, or several parts actually. Okay, so moving on to the next slide. So to start this off, I'm not going to integrate, I'm actually going to show, oh, something missing here. Oh, okay. Sorry about that, these slides are not in the order I anticipated. Okay, first, as I started to say, so firstly, before we do an integration, we're going to do a differentiation. I know that sounds strange, but it all makes sense when we come to it. So if I do the derivative of that, I'm going to get, obviously, 2x2 is going to give me 4x to the 1, and then the 17, because it's a constant, that means anything that hasn't got an x is a constant. It doesn't, remember what I said, it doesn't have to be a number. It could be symbol pi, a constant like pi. It could be any letter that's not an x, h, t, p, anything. Okay, that disappears. It's a constant, so you end up with a 0. And I'm not going to go into the reason why at this point, because we've covered that previously. Okay, so I get 4x. Okay, simple derivative. Right, let's move on. Right, on here we've got integrate the following. So I've got dy plus dx. I've done the integration that you've just seen, 4x. I'm now going to integrate it, and you'll see there that I'm moving back one step. So I've done the integration, I'm moving back one step. I've got my 4x dx. Okay, so the rule is you're going to do opposites. So I'm looking for y. So I'll do my integration of that. Whoop. Let's just clear that off. I have a pen here, I'm using my mouse. If I use my pen, I'll probably do a little bit better. So y equals, so the integration of 4x, I'm doing the opposite functions to what I did when I did a differentiation in the opposite order. So I've got 4x, so it's to the power of 1. We don't write it in as a rule, but it's there, there's a 1. It's a bit faint, 1. Okay, so the last thing I do when I do a differentiation is I take 1 from the power. So I'm going to do the first thing I'm going to do is I'm going to add 1 to the power. Before I subtracted, the opposite is to add. So I'm going to I'll write everything down. It's often best to do this and then tidy it up later, simplify things. So I've got 1, I've added 1 to it, I've got 2. Okay. Right, next step is the first thing you do when you're doing a differentiation is multiply by the power. So I'm going to do the opposite last. So I'm doing the reverse order, reverse function. What's the opposite to multiply? Divide. So I'll divide by 2. Okay. If I do some tidying up, simplifying, 2 will go into 4 twice, so I'll have 4x2. Okay, so I'm back where I started, or am I? Let's have a look. 2x2, but you may spot that I've got a 17 there. I haven't got that here. So what the convention is we need to define that there could be some other information that's missing that we don't know what it is. So we have to write in something to cover it. So what we do is we put in the letter C for constant. It means there's some constant, some missing constant, which may be 0. There may be nothing there. It could be a minus number. It could have been, we know ours was 17, but it could have been minus 17. It could be minus a million. It could be plus a billion. It could be anything. We don't know what it is, but we have to put it in there to remind us that something might be missing. What you can actually do is sometimes in some situations you can actually work out what it is, because you might be given some initial conditions. For example, y could equal 2 and x equals 0, and then you'll be able to put it in and do some solving and find out what c is. But we're not going to be doing anything like that in this video. Okay, so don't forget your c's of constants. If you're German and watching this, you're probably aware that you probably use a k for constant. In English we use the letter c and so on. Okay, let's have a look at some examples. So let's integrate the following. So as long as you can, if you can differentiate, you can integrate. But I have to be honest with you, it's very easy to get confused, especially when we come to the trig functions, as we'll see in time. It's a bit like when you learn to do something and then you have to do the opposite, then it can be tricky. I'll give you an example. I got a new car well, an old car actually, recently, different car shall we say, and the indicator and the headlight switch controls were on the opposite side of the car, so they moved from the left to the right and the right to the left on the stalks. And I've had that car getting on for 10 months now, and I'm still sometimes flashing people when I want to clean the windows. I'm still going to indicate, and I'm turning the windscreen wipers on, that kind of thing. I'm just about getting there, but now when I drive a car the other way, then I'm back to where I started, all confused. So you learn to do something one way, it becomes instinctive, and then when you go backwards, it can go against the grain a bit. Anyway, you'll see as we do it. So let's have a look. So we've got 14x to the 16. Okay, so the first step is in integration is to add 1 to the power. So we're going to get, so I'm going to put the full amount down. So 14x, add 1 to the 6, we've got 7. Okay, next thing, we then divide by the 7, the opposite to differentiate, so we divide by it. Okay, and then we've got our, don't forget your C of constant to represent anything that's missing. We can simplify this, of course. 7 goes into 14 twice, so we've got, so I can simplify that down to 2x to the 7. Now, I didn't say this on the last slide, but you can check your work by differentiating it. Let's not forget the C, by the way. If I differentiate this, the 7 goes down to the front, multiplies it. I've got 14x, take 1 from the power, 14x 6, back where I started. The C is a C of constant, there's no x after it, so that disappears. So back to where I started. Okay? Right, let's look at the next one. So cosine. What would we have to what would we do when we differentiated something? What would give us cos x? That's simple enough. It's sine x. Like that, plus C of constant. And again, if you're not sure, differentiate it and see if you end up back at the integral. So the differentiation of sine x is cos x. The differentiation of C is 0. Okay, easy enough. Next one. So e to the x. So this is, remember this one? Differentiate e of the x, you get e of the x. So if you integrate e of the x, guess what? You get e of the x. It's the world's easiest integration. Plus c. And if you're not sure, integrate it and see if you end up back where you started, and obviously it will get you back to e to the x, the c will disappear. Okay, let's look at some more trickier ones. Oh, now for some trickier ones it says. Okay, 2e2t. Now, I've used a t this time. Don't let that worry you. It's just telling you what the variable is. If I didn't use the dt there, I wouldn't know what my variable was. If I didn't have that there, I could think that it was an x, and then I'd have to deal with this in a different way, which we're not going to look at the moment, but I'd have to deal with it a different way, and I know that my variable is the t. It's just another way of saying x if you prefer, okay? So t is my variable. So the same thing again, right, we know that when you do a derivative of, say, e to the 2t, the 2 comes down to the front as a multiplier, but we're doing opposites, remember. So the opposite of this, and I'll write it down, would be to divide by 2 instead of multiplying. Plus c. Okay, hope you follow that. So instead of multiplying, I've divided, because that's the opposite, and there's only one function carried out in this kind of exponential, doing a derivative of this exponential. Simplify that to the 2 will cancel out, the 2's at the front, and divide will cancel out. I'll get that, and again, if you differentiate to check it, you'll get back to where we started, because the 2 will come to the front. Right, now it gets a little bit trickier. This one. So again, when you were doing a derivative, the power came out to the front and became a multiply. What's the opposite to multiply? Divide. So we've got 4 cos 2t. Again, the variable is a t. All divide by, not multiply, divide, because we're doing opposites, by 2. Plus c. Again, don't forget your c's. I'll keep saying that. I sometimes forget, to be honest with you, but we won't talk about that. Okay, the 4 over the 2 will cancel down to 2. Of course, oh, I've made a mistake, haven't I? It's not, what's the derivative of cosine? It's the derivative of sine is cos. I'm going backwards. So this here, I'll cross that out to show me foolishness, should be sine. Okay. If you spotted that, well done. Let's just get rid of this bit, just to at least get some of it right. Okay, so this would be, so simplify the 4 and the 2, divide it in, I'll get 2 sine 2t plus c. Okay, if I was to do a differentiation of this, the 2 would come to the front and then end up back there with a 4 cos 2t. Right, this one here, now we've got an issue here. Well, we haven't got an issue, but it's easy to trip up, because when we do a derivative of cosine, we get minus sine, but this hasn't got a minus sign in front, so that means it must have started with 1. So it's going to be 2 cos minus cos 2 pi 2 theta divided by 2. Now, the way I recommend doing these is, when you've got the minus sign, it's easy to get confused. So there's 2 things you can do. The first is a good idea, that is to differentiate it. Let's not forget my c of constant. Differentiate it and see if you end up back where you started. So this 2 would come to the front, cancel with this. This would become a plus sign because we've got a minus sign. Remember, if there was no minus sign, it would be minus here. Okay, so don't trip over that. And my recommended way of doing these is do them in bits. And what I would say is, I'm just going to delete this and do it again. Do it in steps like this. So what I would recommend is, you always know when you've got a sine function or cos, it always becomes the other one. We'll call it the other one. It's not the opposite, so be careful not to call it the opposite, because it isn't. Cosine is not the opposite to sine. If anything is, it'd be the inverse of sine. So the opposite, not the opposite, but the other one is cosine. So write that down first, because you know that's the bit I forgot in my previous example. So it's a good place to start. The other thing we know is the stuff inside the bracket always stays the same, just as it does when you differentiate. So do that next. Then do your bit. What happens to this? It becomes a divide. So progressively it's getting to the more tricky bits. Then think about your signs. And by that I mean the negative and positive sign, not this sign. Okay, so again, it would have to have started with a minus sign for this to be a positive sign here. If you understand what I mean. And don't forget your letter C for constants. Okay, so fairly straightforward, but that's when you first start doing this, that's one of the easiest places to trip up. And as you've already spotted, my big weakness is, if I'm not careful, I forget to change the function from a sine to a cos, or from a cos to a sine. Okay, so let's have a look at some more. So these 2 here. Now this one here, I've gone to t, I've got 4 pi. Now pi is just a constant. So this bit here, 4 pi, is just a number, so don't be intimidated by it. But the reason I've done it is because it's more likely what you're going to get when you're doing differentiation and integration, because we're talking about sine waves. When you're doing a calculus, it's going to be in radians. Remember that, always in radians. And as soon as you see the letter T for time, assuming it is for time, then you're going to be in radians, and it's always in radians anyway with calculus. Okay, but in general trigonometry functions, t means time, so it's going to be in radians. Your pi is definitely for radians, pi is radians basically, so it's going to be 4 pi. So don't be afraid by the fact that you've got this 4 pi here, because that's just some number. 4 times pi gives you a number. So it's the same steps. So let's do it the way that I just said on the last one. The opposite function is going to be cos. The stuff inside the bracket always stays the same. Excuse me while I tidy that up. 4 pi t, close the bracket, so no change there. Then we divide by it, not multiply, so we're dividing by 4 pi. We've got the 8 in front, don't forget the 8 in front. I should have really done that before I did this bit really, because we can always tidy that up at the end. And sine, so if you differentiate cos you get minus sine, there's no minus there, so there should be 1. Let's put that in. If there'd been 1 there, there wouldn't be 1 here. Okay, it always becomes the opposite that way. And then plus c, and then let's tidy it up. The 8 will cancel with a 4, so we'll get 4, don't forget the minus sign, 4 cos 4 pi t plus c. Now on this one, I'm actually going to jump straight to the answer, give you the answer, then talk around it a little bit, explain a little bit more about it. So the actual answer would be, oh, that's better, pen problems there. So the final answer to this one would end up being log of x. Let's try putting the pen on as well. Log of x. Okay. Think about it. What would give you log of x? If you were differentiating log of x, you get 1 over x. So obviously 1 over x must be log of x when you integrate. Now there's an important point here. If you had, I'll just work over here, 1 over x to the 2, to integrate that you would have to convert it into this using your laws of indices. And then when you integrate it, you would get x, so you'd add 1 to this power, you'd have minus 1, and then you divide by 8, which actually would end up being minus x to the minus 1, which you could change back into minus 1 over x if you wanted. Okay. Now if you do this with, I'll just remove some of this. I'll try. Just take this out. If this was like my example, that would be minus 1. Okay, what do you get? You got minus 1, you take 1 away, you've got x to the 0. Right, now then you bring this down as a power, you're dividing by 0, which is not allowed. And that's what, you can't do it, and it's just as well that there is actually this correct answer here, which is log of x. So just remember that. Don't try doing this, don't try to be over clever with it, because you just end up in a mess. You just end up breaking one of the laws of maths basically. So this is the way of doing it. Okay, which brings us very nicely to the bit I know you've all been waiting for. Your turn. So I'm going to, what I recommend you do is I'm going to give you about 10 seconds. So if you pause the video in a second or two, and then turn it back on, and I'll give you the answers on the next slide. This down here is a 2, so it's 1 over x to the 2. Okay, and then pause it, and then in 10 seconds or so I'll give you the answers. So if you want to pause it at this moment and have a go if you want to. Okay, thank you. Okay, welcome back. So hopefully you managed to do all those okay. So here I've put the answers. The first four are straightforward, so I'm not going to discuss them. This last one, remembering what I said on the last slide about the x to the 1, I did show an example with an x to the 2. You've got to convert it to this. So that was the only tricky one really there. So you've got, ends up being minus x to the minus 1 plus c. Okay, thank you for listening.